Walk me through how you kind of TensorFlow, how you this first part was where you're too much about.
Testing. Can you guys hear me now? Is that better? Okay, perfect. All right. So I'll rapid fire just for anyone who missed out online. So in this chapter, we're talking about TensorFlow and Keras and training models. And this notebook was written when the book came out. So it's a little bit old. And so I went through and I updated some of the versions and stuff. So if you look at the GitHub of the official book, a lot of the stuff you actually try and run it and it breaks. So I went through and I tried to just update all of the stuff that might be problematic. Um, so the chapter started talking about tensors and the different operations that you can apply to them. So if you're familiar with NumPy or any of the other numeric computing libraries, you have this concept of like an array, basically. So this tf.constant is what lets you define an array or a matrix or whatever kind of data structure that you're trying to do. And so constants, you put some values in and then they're constant, so you can't change them. They're immutable. um, so you have to be careful with those. They aren't that capable. Most of the time you'll probably want to be doing stuff with tf dot variables you can actually change, and they're what's useful when you're doing neural network training. um, so in the notebook, I'll just start running this so we can see all this stuff live. So we have constants and we can define it in various different shapes. So in this, we can see they made this like list inside of a list, and then it defines a matrix that's got this shape and these values. Um, and then they also show you can make one that's a constant that's just set to 42. It has no shape. It's just a single value. You can see its NumPy value is 42. And then you can see now they have the list inside of a list, and then you see it has this shape 2 by 3, and then it has um, the array that has 1 2 3 4 5 6. So we can look at the shape, we can look at the data type. So its data type is by default float 32, so that gives you a certain amount of precision. You can represent a certain set of numbers with that. um, and then they show that you can do indexing like you do with NumPy. So you can say grab all of the rows and just this column, or all of these columns and just this row. You can index it in all kinds of different ways. um, so they didn't go into that great of detail. They kind of assumed if you've interacted with NumPy, it's basically the same thing in TensorFlow. Um, and then they show that you can do all these different kind of operations. So this is showing that if you have some sort of variable or constant, you could do t plus 10, and then it will output something new for you. So we had that array that was originally uh, up here 1 2 3 4 5 6, and then if you add 10 to it, then you end up with 11 12 13 14 15 16. So you can see you just added 10 to every element in the array. um, you can do square, you can do transpose, you can do matrix multiply. So a lot of the stuff that you would want to do with your math library, you can kind of just write Python and it will figure out what to do it. And then there's certain functions for stuff like square that might have a baked in like TensorFlow versions that you can do that stuff. Um, so a lot of the focus will be on Keras. So the way that I would describe TensorFlow versus Keras, so TensorFlow is the like lower level numerical computing library that helps you do all of the nuts and bolts, like add great granularity. And then Keras is kind of this wrapper that helps you do things much more easily. So you don't have to be as verbose. You don't have to write everything out in great detail. So when I first started, I started with Keras, and it was a really good way to be able to like play with things, but not at like super deep detail. You could kind of say like, okay, start with this model and then do dot fit. And I didn't have to know all of the details that were happening, but I could still do something useful with it. Um, so Keras is very useful. And so this is basically showing that Keras is it can interact with the TensorFlow backend, and you can do all of the same stuff, but then it's the Keras form instead of the TensorFlow form. So they also show that NumPy being very similar to TensorFlow, you can go back and forth between these. So if you have a NumPy array, you can send it over to a TensorFlow constant. So they're showing, okay, I make a NumPy array of this shape with these values, and then they say just wrap it in a constant, and then all of a sudden you have the NumPy form swapped over to TensorFlow. And so one of the nice things with doing this is because there's really good interoperability between NumPy and TensorFlow, if you want to do something on NumPy, it's limited to CPU. If you transfer it over to TensorFlow, then you can push it to GPUs or TPUs or any other kind of computing device, and then sometimes it will be much faster. So sometimes you do something in NumPy and you go, oh, this is too slow, and you can do a very simple wrap of it with something like this, and then all of a sudden you get this magic speed boost because it's running on a different device. So you can go both directions. So one thing with TensorFlow is it covers a lot of the same ground as NumPy, but it might still be missing something, or you might need it in NumPy for calculating some metrics or doing something else. So if you want to, you can always just do .numpy, and then it will just pop out a NumPy array again, and then you have a nice form that you can do whatever else you want with NumPy. So one of the things that they talked about in the book was one of the rough edges is if you have differing data types. So if you have a float and an integer, or if you have different kinds of floats and then you try to add them together, you'll end up just getting errors like this. So you have to be kind of careful and say, okay, if I'm adding these values together, if I'm multiplying them, if I'm doing some other operation that concatenates them or something, I need to make sure that they're the same data type so that they match up together. So one of the other things that they showed that isn't really that common is you can also do TensorFlow strings. So typically, most of the stuff that you do in TensorFlow is going to be numerical. So if you put a string inside of a TensorFlow constant, you're kind of limited in what you can actually do with it. So it's not that common to put a string inside of a TensorFlow constant or variable or anything. It will automatically encode it to UTF-8. So we see it as the regular string, but then in the back end, it will convert it to some like UTF garbage that we can't really understand that well. So I'll skip past most of the string stuff. One thing I will mention is that text is something very commonly that you interact with. And one of the things that you will run into is ragged tensors. So ragged tensors is this idea of like, sometimes you have a matrix and it's very nice because every row has the same number of columns, or all of the columns have the same number of rows, vice versa. But when you have text, every sentence doesn't have the same number of words, for example. And so if you split it up like that, it doesn't work very well. So there's this concept of a ragged tensor, which is basically saying like every row can have a different amount of content inside of it, and it's perfectly fine with that. If you try to do that in a different matrix, you might have to pad everything to be the same length, or truncate everything, or have some other way of handling that. So ragged tensors are how you handle that when all of a sudden you have like all of these different shapes and it makes things messy. The other thing that they showed was sparse tensors. So you might come across some scenario where you have a matrix that is mostly zeros and then only some values are actually filled. This is also very common in like text data. If you have a matrix that's saying, here's our whole vocabulary and how many times they occurred, it's very likely that you have a vocabulary of 50,000 words and only 30 of them are used in a sentence or something. So it's very inefficient for you to have a value in every single column. So instead, what you can say is basically store it as indexes, saying, okay, I have a word here, I have a word there. So that's what sparse tensors are used for. Um, One thing they show that you can go from sparse to dense. You have to be careful with this though, because if you have something that's sparse and you go to dense, then all of a sudden it takes up way more memory. Um, so sparse to dense can be potentially just kill your computer if you have the wrong shapes. So you have to be careful with that. Um, So they're showing that you can also do sparse dense matrix multiply. And this is nice for if you have something where you want to actually multiply these together, but you don't want your memory to blow up. So it's this operation where you can basically, I have a sparse set and then I'm multiplying it by something else. Um, I wouldn't really worry too much about the details of that. That's one of those like uh, detailed things where once you hit it, you can figure it out, but it's not something you'll run into that often. Um, One of the other things they talked about was the sets. So sets are useful because you might have like a set of something and the order actually doesn't matter and you just want the union of all of the things. So you want to say what is the set of vocabulary, for example, what is all of the possible words out of my set. um, so another thing that it's in the library, but it's probably not something you'll actually interact with that much. So at the beginning, I mentioned that there's constants and there's variables, and variables are probably the most likely data structure that you'll interact with a whole bunch. So variables are, you can actually change these. So if you set it to 1, 2, 3, 4, 5, 6, you can reassign it with something else. So like this example that they're showing, we have an array that's tf dot variable and then this data in this shape, and then they say we can assign a new value, and this new value is going to be 2 times v, so whatever the original was. And so with this we can see all of the values got doubled. So it was 1 2 3, now it becomes 2 4 6. It was 4 5 6, and now it becomes 8 10 12. So that's the major difference between constants and variables. It's variables you can actually change and do a bunch of operations on. Um, so variables is probably what you're more likely to interact with. They're showing that you can do the same indexing thing that we were talking about earlier. So you can say, grab the zeroth row first column and then assign 42 to it. And you can do all of this sort of fancy indexing that you would normally do with NumPy. Um, they also show that you can do this scatter n-dimensional update, and you can basically say, do multiple updates at a single time. So you can say, define all of the coordinates you want to change and all of the values that you want to set them to. So they're saying at 0, 0, make it 100, at 1, 2, make it 200. And then they also show the index slices and the scatter update. And so what this is showing is saying, okay, set these values at these indices as well. Tensor arrays, I'm not as familiar with. So this is basically saying make a data type and then make it of this size. And then you can write 2 of them iteratively. So my assumption is that it actually starts empty and then you're kind of plugging values in. And so it allows it to be flexible in that way. So then getting into the actual neural network part of this, they were showing like this is all showing the custom things that you can do with TensorFlow and Keras on top of the basics that we've learned previously. So they show this example where we want to define a custom loss function. So what they're doing is they're saying, okay, import this California housing data set where you're given some variables about a house, and then you want to predict what is the price of the house. And they're importing other scikit-learn stuff just to do some scaling and splitting of the data. So they pull in this data set and they split it into train, test, and then the labels that are corresponding to it. And then they scale it. So what they're doing is they're saying basically your input variables, you could have like square feet, and that's 2000 or something like that. And then you have number of bathrooms, that's 2. And then you want to scale them so they're all on a similar scale. So the part that they're really trying to show with this example is this Huber function, this Huber loss function. And so this is actually something that's already in Keras, but they just wanted to show this as an example of something that you could do. So if you wanted to do a more custom loss function, you could define it in this way. So what this loss function is doing is it's basically saying when it's under a certain value, when the loss is under a certain value, treat it in a certain way. When it's over a certain value, treat it in another way. So this is important when you have something where like a scaled value makes the loss massive, and then you actually care a lot about the small portion when it's getting stuff closer to correct, because you're squaring it in some way. So if you have a value that's 0.1, then you square it and it becomes tiny, and then you have a value that's 100 and you square it and it becomes massive. So showing this example, they're showing what this loss function looks like. So basically showing that between -1 and 1, it's at some certain curve, and then beyond that, it's curved in a different way. So one of the things that you have to do with Keras is you have to define some input shape. So this is the number of variables that we're looking at. So the house, it might have the number of bathrooms, the number of bedrooms, the whether it has a pool or not, how many square feet, all of this different stuff. And you need to define that as the input shape of your network. And so we've looked at this in the past. So these Keras models sequential, you can basically say make a certain input shape and then all of the different layer shapes after that for your neural network. And this one, they're making it simple. They're just saying make it a single 30 unit dense, and then reduce that down to a single dense output. So you have a single output saying what's the house price, basically. So this is their definition of their network. And then the way that you do training is you do model.compile. And when you do compile, you can see I've hovered over it. You have to define an optimizer, a loss, and you can optionally define a whole bunch of other stuff. So in this case, we're able to define our loss as this custom loss function that we defined up here. So this Huber function. You could say just mean squared error, any of the losses that are already existing, or you can plug in this loss function that we defined, as long as that loss function matches the kind of template that the loss function should follow. So you give it an optimizer, and then we can define the metrics that we're looking at. So that compile step is just basically saying, gather up all that stuff. This is what I want my training run to look like. And then when you actually say .fit, you pass it the data. So you say, here's the input, here's the output, here's the number of passes of the data that I want, here's the data that I want to validate against. And then you run this, and it runs for 10 seconds. And so it does a whole bunch of training steps. And then you see the mean squared error, the validation loss, the validation MAE, and that's the whole training setup.
So just one quick comment. They're easing us into this customization, and so they started with the loss function because by using it with Keras, we just wrote a regular Python function with some inputs. There's no special anything. There's one little caveat in terms of you want to write it in a way that it works well with vectors or tensors, not just scalar inputs. But this is how this is the big takeaways. They're saying like, hey, you're not really gonna need to learn a whole lot of new stuff. We just wrote a regular Python function here, and automagically the library did everything for you.
Yeah. So this is what I started learning ML with, this whole compile and .fit. And so the way that I would think about this is like I just had to define a few different things. So I define the loss function, I define the optimizer, and then I do .fit, and it just in the background is doing all this magic for like, how do I load the data? How do I make it into batches? How do I do So this is abstracting a whole bunch of stuff away from you, but it's very useful because if you look at like how much code was actually written here and how much it's actually doing, it's very nice to have it kind of just separated away from you. Like this loss function, we could do really anything fancy inside of this, and all we have to do is say, okay, we know we have some labels and some predictions, and then I return some number back, and in between I can do whatever I want basically. So if you want to swap out a loss function, is very easy, and you don't have to worry about all of the like actual internal details of that. So that's the model.fit. And so this was one of the pieces that I had to change. So they changed from an H5 format to .keras now, I guess. And so I had to swap out some of the saves and the loads. So one of the things that they're showing that's kind of a rough edge of TensorFlow and Keras, I would say, is we save this model out, and it doesn't save everything. So it's saving the weights, it's saving the model definition, but it's not saving some of the custom stuff that we did. So we save this out, and then when we load the model back up, what they're showing is that it didn't package up the Huber function as well. So that custom loss function that you defined, you need to redefine that. You need to make that part of the package again. So the way that you do that is you say, here's some custom object I want to bundle back into this setup. And so you say, okay, it's named Huber function, and here's where it's defined. So you have to make sure, okay, I carry that code forward because it's not actually bundled as part of it. One of the notes that they put in the book was saying there is a way that you can register it and make it saved as part of the bundle itself, which I think is good, but it's a little bit like it's tricky when someone else trained a model, they saved it, and then they give it to you, and then it's like, I'm missing this function and I can't run this model anymore because I need to also have whatever code that was missing as well. So this little bit, they're just showing, look, we saved it, we reloaded it, and when we keep the Huber function around, we can run training again. If we comment this part out, then it tries to run and it says, oh, I don't have a Huber function, it's broken. So one of the things that they showed was that Huber function in that one, we set the cutoff point to be 1, so -1, 1. But in theory, you might want to actually change that value. So if your cutoff point is 10 or something like that, then you might want to set it to something differently. So the way that you can do this is you can say, okay, create Huber, and then define some threshold value, and you pass that in and say, change what I want it to be. So they're saying, let's set it to 2 instead of 1, just as a simple example. And so what this is doing is it's calling this function and it's making this loss function with a new value swapped in for this threshold that we're cutting off based on. And so this is just showing that these things you can kind of store extra data and make it a little bit more flexible. So with this, it's running the same thing. It's just set to 2 instead of 1. And then this is the same thing where we save it, and then when we reload it, we have to reload it with whatever value. So it's not actually stored as part of the bundle again. You have to say, okay, I know I have this create Huber function that's making this loss function that has this threshold that's defined. So there are ways to bundle all of this together, but it's kind of a hassle. I think that's one of the worst rough edges of old TensorFlow and Keras. So one of the other things that they're showing is like we did that manually, but there's also this way that you can inherit from all of the Keras stuff. So this gives you kind of the template of what it's supposed to look like, and then you're just overriding certain pieces of it that you want to change. So this is the like proper Keras way of saying, okay, we want to set some threshold and we want it saved to this value. So now it's part of the loss. It's a more permanent value. And then this call is what is actually run when we call this loss. And then this get config is the part that is defining that threshold. It's saving this object as threshold set to a certain value. So they've shown in great detail multiple different ways that you can do this thing. That's one of the complaints that some people have with TensorFlow and Keras is TensorFlow has tried very hard over the years to keep backwards compatibility with all of the previous stuff that they've done, and the way that that has panned out over time is uh, they have certain stuff that have 8 different names because they've gone through all of these different iterations. So that's one of the difficulties with TensorFlow and Keras and all of these related packages. So they've tried with 2.0 and all of the new stuff to condense things down and have an actual recommendation of the way to do things, but it does like kind of bring forward some of the leftover pieces from previous iterations. So next they're showing like we defined a custom loss function, but you can also define custom other pieces. So if you want a custom activation function, if you want a custom initializer that sets the weights at initialization, if you want a different regularizer, if you want some constraint applied on top of your weights, so make my weights always positive or some random thing like that, you can define all of these other pieces as well. I think that works fine. So that was one of the rough edges that I had to change. They had updated some of the naming of some of this stuff. So one piece that I do want to show is like this information is in the book, but the true like source, if you want to look up what something comes from, the documentation website will tell you all of these things. So if you want to understand in more detail, you can see stuff like this. So they say, okay, kernel regularizer, bias regularizer, activity regularizer, like this is where you actually properly learn all the different pieces. And I wouldn't start by going through and reading every single page of this, but when you run into an error like I did, that's the way that you solve it. And very often, I don't know if they have any examples here, but very often they will actually say like, oh, breaking chain from version 2.4 to whatever. And so if you run into some error, you can typically find the page and say, oh, I either need to run an older version or I need to update it to some change that they made. So this is just showing, look, we can do these custom things and we can compile and then we can run training again. And we can do the same thing where we save the model. And then when we load it back up, we have to do all of these different custom pieces that we defined before. So now we have multiple different pieces that are missing, and so we have to bundle that code in somehow to keep the model functional. Otherwise it loads it and it says, oh, I don't have this thing that I'm trying to run. So this is just more examples showing the different things that you can set. So in this one, they were showing like we can change the L1 regularizer. We can define these in a bunch of different ways. So that was all of the kind of like weight impacting things. But then the other thing that they were showing is that you can do custom metrics. So the difference between losses and metrics is the loss actually impacts the training of your model. So if you define a new loss function, then it's going to say, okay, update my model weights in some different way. Where your metrics is just something that you're measuring just to kind of have some understanding of what's happening with the model, what is the performance of the model. And so these things will be calculated, but they don't actually have any impact on training necessarily. So metrics are more flexible because they can be non-differentiable. They can be completely like open domain, whatever you want to have defined there. So metrics wide open can be whatever you want, basically. They can be loss functions or they can be just basically any Python, any TensorFlow code that you want. So in this example, what they're showing is that you can define metrics like, so they're using this Huber loss function with 2 set as the threshold. But with metrics, what you can actually do is you can have a whole list. So you can say basically, I want to have you measure accuracy and F1 score and mean squared error and all these different things. And you just define it as a list saying, measure all of these things and report back to me what they are. And then it tells you like, okay, how is the model learning over the training iterations and everything. So this is showing the model fit, and then this is showing, look, it's measuring this Huber function as one of the things during training.
So another just quick color comment. So they started off easy with things that are stateless. And so if you just want to do a TensorFlow equivalent, you just write Python function. And again, auto-magically, it turns everything into what you need. We're going to see, I think, in the next part of this metrics example, is some metrics are sort of stateful. They keep track of things across the entire epoch to do like an average, whatever. And all of a sudden, now that you have state, you can't just treat this as vanilla Python code. So from here on out, we're going to deal with things where you actually need to have TensorFlow variables and state that you're tracking. So it's going to be a little bit more complicated. I think even if you're working primarily in PyTorch, the concept of, oh, I have something that's stateless, PyTorch will just automatically convert my Python code into, PyTorch stuff that can run on GPU. But as soon as you have state, you do have to think about how are you actually doing this. So it gets a little bit more complicated.
Yeah. So that was the basic custom metrics. And so in these, it's saying every single one of these is independent. If I just had this in isolation, I can measure its performance. But then you have other things, like I was mentioning, F1 score, precision, recall, all of these other things. They're actually aggregations across all of your data. So if you do it just like individual sample at a time or batch wise, when you average it together after, it's not exactly the same thing as if you actually aggregated the entire data set and then measured your metrics. So that's one of the more complicated things that you can have. And so the way that they call this is streaming metrics. So it's metrics that say like, okay, gather how many false positives, how many false negatives, how many true positives, how many true negatives, and gather all of these up over time. And then at the end, we'll like piece those together and say, what's the precision. So these streaming metrics, it's saying throughout the whole training run, throughout all of the validation, just gather all of these things up. And then at the end, we'll calculate what's the value. And it can live do all of the subsets and say, okay, during training, we're giving you updates, but it's the accumulated updates. It's not individual batch at a time. So this is they're showing, okay, we have this precision value, and then they give it a list of labels and a list of predictions, and they say what does this individual thing do, and then they say give it another set, and this is actually an update of the previous step. And you can see when they do dot result, it's the accumulation of this batch plus that batch, and then they get a value of 0.5. And so if you look at the variables that underlie this, so what they have to do is they have to keep track of the number of true positives and the number of false positives, and then they can fit that all together in order to figure out what the actual value is at the end. So they say we have four true positives, 4 false negatives, and that's how we get to a value of 0.5. And that might be a little bit confusing because you're saying we have this batch that's getting 0.8 and this batch that's getting 0.5. But when we aggregate them all together, we end up getting a 0.5 value again. So that will accumulate all the values, and then eventually you have to clear it out because you're on a new epoch or you're doing validation instead of training or something like that. And so what you have to do is you have to reset the state. And what that will do is it takes all the variables and just says, go set them back to 0 or whatever their default value was. So this was the like official Keras precision streaming metric. And then here they're saying, how do we define that for our own things? So if you want to define your own, then you have to decide what variables do I have to keep track of in order to accumulate my different amounts. So in this Huber function, they're just saying, okay, we're going to define a threshold. We're going to define what the actual Huber function is. And then we have a total that we're calculating over, and then we have a count. And so what this is going to do is it's going to say, keep accumulating the total, keep adding 1 for the count every time we see data. And so what this is showing is you're updating your state in little steps. So every time you're saying update state, and it's adding to these values. And then when you call result is when it actually calculates the total over this. So Huber function, you can do that individually piecewise, and that doesn't matter. But they're showing here's how you build up a custom streaming loss metric, custom metric. So this is the Huber metric, and they're just showing what happens when we add values to it. So they're saying, okay, 0, 5, 1, 9.25. And so it's comparing 0 to 1, comparing 5 to 9.25. And then when we're doing the result, it's saying, okay, do the total over the count. And then that's what gives you this value of 7.0. And then they're showing the same thing. So we have the variables, and our variables are that total and that count. And so we can see the total was 28, the count was 5, and that's what gives us that value that we saw here. And then they're showing when you reset the state, it set them back to 0. So it was 28 and 5, we reset state. So now they're 0, 0 again. One piece that they didn't really talk about, but I would say is pretty important, is this Keras.backend clear session. That's very useful if you do something and you run out of memory and you say, okay, just start over, just clear memory off the GPU and just have open space again. So they didn't really talk about it, but this is a pretty useful function just to remember the name, because you do training and then you run out of memory and it dies and you say, okay, I need to recover from this some way. So you typically do that with clear session, but then you have to go back and say, redefine my model and everything else, because it gets wiped out of memory. But it's a useful function, especially in a notebook like this, because you're going top to bottom and defining all these things, and you can periodically just say, okay, like clear off the working space, basically. So this is showing we defined the custom metric, the Huber metric, and so define the model, compile it with our custom streaming metric, and then train on top of that. And so runs really quickly, and then we get our values back, and we can see that each epoch is returning a value for us. So same thing as before, we save it, we reload it, and when you do that, you have to redefine these things again. So you have to say that this was missing, fill in the gap again, and they're just showing we can train again. So one of the mentions in their notebook was saying that these things have been updated. So if you have some old code, it might kind of silently do something weird where it pulls from the last instead of the first. And so just one of those breaking changes that has happened over time. So this is showing when you do training, you get back these values and you get back a dictionary defining all of these different things that you might be interested in. So this history is saying, here's the values from all of your previous epochs. So in all of these, we've only been doing 2. So we just have this one and this one. But when you pull that out, you might want the sequence of all of the losses, or the sequence of all of the metrics or learning rates or anything else. So this history is what gives you back that sequence of everything. So this is useful if you want to make a plot and say, like, okay, what's the loss curve look like? Is it still going down over time? Is it very bumpy? Is something chaotic happening? So then the next section, what they started talking about is custom layers. So in the past chapters, we've talked about the models and all of the different layers that are directly built into TensorFlow and Keras. And so that already covers a very wide surface. It's not that likely that you probably want to start off by making a custom layer. But this is useful in case you want to bundle certain things together. So the place that I would see this actually being used is that people might take an entire model. So they say, like, oh, someone pre-trained this on ImageNet or something. And then you take that whole bundle and you treat it as if it was just a single layer. and then you tack some other stuff on top of it. And it's nice to be able to say like, this thing was 30 layers. I don't want to have to define all of them. So what I do is I just say, okay, this block, make that a layer, and then just make that my first layer or something like that, when in reality it's actually a whole bundle of things together. So this example, what they're showing is you can take different pieces and you can wrap them and you can say, make this just a layer. So it can be any TensorFlow math that you want it to be, or it can be multiple layers that you're wrapping into a single layer. It can be a bunch of different stuff. So in this, what they're saying is basically we want to take this exponent function and just make it a layer. So in this way, it makes it so that you can say pass through this, and then when I hit this certain part, just exponent it. So what they're showing is in the previous ones, what we've done is we have one dense layer that has 30 units, and we have one output unit saying predict the stock price. And what they're saying is, well, maybe it's useful if you do an exponent layer. And so this layer is saying, take whatever that output is and just take it to the exponent. And in this way, your model's output is kind of scaled in a non-linear way that might be useful for something like house prices, maybe. So in this, we can see it's training over time. So they did 5 epochs, and it's going down, going down, going down. So one thing that they warned with this is that there can be numerical stability problems. So when you do exponents, when you do 1 over x, when you do a bunch of different kinds of things, you can have problems where you actually run into like the numerical threshold of what can be represented by the data type. So if you have float 32, then you have a certain maximum value that you can represent, and you have a certain smallest value that you can represent. And so that can cause problems. So one of the things that they warned is like actually doing the exponent this way is kind of dangerous. You probably don't want to do that because it can cause it to overflow or underflow or cause other problems. So they also show the other way that you can define layers. So the first way that we did it was with this lambda. So this lambda, you're kind of limited because it can only really be a sort of one-liner thing nicely. But the other way that you can do it is with inheritance and subclassing. And so the way that this works is, I mentioned it earlier, you can say basically, here's the template of what a layer is supposed to look like, and then just overwrite certain pieces of it. So if you want your modified dense function, it can look something like this. So what you're doing is you're saying define how many units you want, define what you want your activation to be, and then you can build it to initialize in a certain way and certain kind of bias. And so you can modify this all up and do whatever you want with it. So if you want the call to be shaped differently, if you want its output shape to be different, like all of these things will just kind of do whatever TensorFlow thing you want inside of them. So you can just do custom operations inside of there. So in this, what they're showing is you can even have multiple layers become a single layer. So that's what I was saying earlier, is you can basically say this layer thing, it's kind of loose. Layer doesn't mean single operation or anything like that. Layer can be a whole bundle of layers. And one of the things that they were mentioning in the book is that like, if that's the case, why wouldn't you just call everything a model? So everything's a model, even if it's a single layer, and then you just stack everything up. And so you can do it in that way. There's nothing preventing you from doing it like that. Models and layers are kind of interchangeable, but it's nice to be able to kind of separate them and say like, here's my set of layers, and that builds up my model. There's a certain hierarchy and structure to that. So this is showing we can make a very flexible representation where we're saying, okay, we have this multi-layer setup and it takes 2 different inputs. And we did this with subclassing very very efficiently. If you look at how much code was actually written here, it's only 5 lines, 6 lines, something like that. So they're just showing basically all of the different passing the data through it, what's the input shape, what's the output shape, and all of the different ways that you can bundle these together. So one of the things that they're showing is with this setup, you can actually have additional like stuff tacked onto this. So you have your like my multi-layer thing. So they define this, and you can start by thinking of that as a model, but then in this setup, what they're showing is you can actually say, okay, I want my multi-layer to be one of the steps, but then I also add on more dense layers, and then I concatenate those, and then I make another dense layer, so that my multi-layer at one point was a model, but now it becomes just a building block into a bigger system. So we can compile this whole thing, and it knows what the inputs and the outputs are going to be from this step here. And then it knows, okay, here's the definition of all of the steps in between. And then it's fitting, and it does the whole training step again. So one of the things that they were showing is it's actually not limited to, like, it doesn't have to be a neural network layer. It can be like dropout or Gaussian noise or some other random operation. You can consider that a layer. So what they're showing here is you can make a add Gaussian noise layer. So in between all of your layers, you're just making one of the layers be like noise the input. So hopefully that makes your model more robust to some variations, noise in your data, stuff like that. So they're basically saying, when you think of it as layers, you probably think like neural network layers, a dense layer, a convolution, or something like that. But it's really not limited to that. It can be any TensorFlow operation. So they're showing add Gaussian noise with a certain standard deviation, and then go through this same network design that we've done in the past as dense 30 units, and then dense 1 output unit. And then we can show its training again, going through multiple epochs. So now custom models. So very similar to the layers, like I was mentioning, it's kind of interchangeable. You can use layers, you can use models, but they showed this pretty explicitly with this residual block. So they're saying, look, we made a custom layer, and then what we're doing is we're putting that inside of a custom model. So in this one, we're inheriting from layers, and this one, we're inheriting from models. And what this is doing is it's saying, okay, one dense layer, and then we have these residual blocks. We're doing 2 of these, and then we're doing another dense output block. So this custom model is using custom layers, and so this whole thing nests together in order to operate in a certain way. So this model definition then gets passed, it gets initialized, and then it gets passed to the compile, and it gets passed to the fit, and then it also does evaluate and predict, and then we can see what its validation score is, and what its predictions look like. So now they're showing we can use it even in non-custom models. So we define this custom residual block, and then they're showing first we did it in the custom model, but you can also use it in a sequential model. So sequential models we talked about in previous weeks. Sequentials are basically saying it's just this layer into that layer into that layer. It's just all following a sequence. In the custom model, we can kind of do whatever we want. It's just open TensorFlow, but in sequential, you know that one layer is going to get passed directly into the next. So we do the same process: compile, fit, evaluate, predict, and it functions basically the same as the one that we were just looking at. So previously we were looking at certain metrics, and so those metrics were based on the output of the model. So your model makes some prediction, and then it gets compared to what the actual label was. And one of the things that they wanted to show is that your metrics can actually be based on some internal thing inside of your model rather than just the final output, something like that. So one of the things that they're showing is this reconstructing regressor. And so what this network is doing is it's saying, take some input, do some processing on top of it, make a prediction of what the final output should be, so what the house price is, but then at the same time also try to reconstruct what our initial inputs were. So you can think of this as like it's taking the inputs, it's compressing them down, it's making a prediction, and then it's trying to decompress again. So it's trying to get the original values back out. So this reconstructing regressor, we might be interested in recording the metrics of this sort of secondary thing, but we're not actually, it's not one of its final outputs, basically. So in this setup, we can see, okay, we're initializing the model, we're doing the compile, fit, predict, and we can see what the reconstruction error is. And it's going down along with the training loss as well. So that was all of the custom like Keras bits. There's lots of different things that you can mess with. They went in pretty great detail of all of the different pieces that you can touch. I honestly don't think that you'll interact with that many of them. Like the set of options that they give you out of the box is pretty complete. So you can define custom stuff if you're working on a problem and you really need a custom metric that's most relevant to your business. You can do that, but very often, like what you actually do is just say, okay, make some predictions and then do everything outside of TensorFlow or do it as a separate process. Yeah, go ahead.
There was an initializer that was initialized in the upper class, the reconstruction thing. Yeah. What does that does, and like how is that different from like other initializers like Gloret or like some other things that we have? Is there any significance for this?
I don't know exactly why they picked this one, but what this initializer is doing is it's saying what do you want your values to start at, basically. So you have this dense layer and you could start it at all zeros or random noise or some other initialization strategy. And so they're saying set it to Lacoon normal. So I don't know exactly what that one's doing, but it's basically just saying set random weights to start on
Okay.
that layer. Yeah. So yeah, there's all these different pieces that you can build with Keras and TensorFlow. In general, my experience has been like, if you look at what is already baked into TensorFlow, there's lots of options. Like if you look at activations, if you are a researcher and you want to say, I'm researching activation functions and I want to come up with new ideas, you can do like unbounded any TensorFlow functions. But if you're someone who's trying to build a model to solve a certain problem, generally these are going to suffice. You're not going to need to define custom activations or loss functions or anything else.
Yeah, I think that's a great comment. And then maybe the other way in which this is useful is, let's say you don't write this stuff, but you read about a model that somebody built that's like really good for this task that you have. They might have one or two of these custom things in the repo. And so then at least now you've seen it before. So when you see the code, you kind of know how to read the code. And again, the nice thing is that, I mean, early versions of Keras, TensorFlow, PyTorch, it was very hard to do this custom stuff. Stuff got ugly really fast. Most of this code is quite readable. I would say the main way in which this stuff differs if from PyTorch is that the really nice thing in Keras is if you string a bunch of layers together, you don't have to specify the dimensions of the tensors. And that's why I noticed when we were defining that layer that there was this extra function that you don't have in PyTorch, which is compute the output size shape depending on what your input shape is. And so it just automatically does that in the background. It says, oh, you passed me in a, whatever, 100 by 256. Therefore, my output's going to be blah, blah, blah. But other than that, some of that just like bookkeeping of the tensor sizes, it's pretty straightforward. Not bad.
Yeah. So that's all the custom stuff. And then what they wanted to also show was like, if you really look at why TensorFlow is useful, the biggest value is the automatic differentiation. So this is what makes it powerful for neural networks, is basically it can keep track of the gradients as you're building up this network, all of the layers, all of the inputs that you're passing through it, the loss function. It tracks all of this stuff kind of just automatically. You don't have to define a lot of the different things that are happening. But they did want to show that you do have a certain amount of control with this. So when you go and you define your network and then you just say fit, it's doing all of this stuff in the background that you don't have visibility or control over. And you can also do this more manually with like the way they use the gradient tape. So in this way, what they're showing is basically you can define some function, and then if you want to, you could manually do the derivative, and then you know what the slope is at certain points, but it's a big hassle, especially if you have a network that has thousands or millions or billions of parameters. You can't realistically do that. So that's what the value of this auto differentiation is. So this example here, what they're showing is one of the analytical method is saying, okay, look at the formula and figure out what the partial derivative is for all the different variables, but that becomes crazy when you have a lot of variables. And then the other method that you can do is you can say vary the value by some minuscule amount and say, okay, I went up, I went down, and then that gives you the local slope as well. But that's also prohibitive when you have many parameters. So the way that this differentiation works is very, very useful because you can actually apply it to massive neural networks, and it's very efficient and can get you exact values. So this gradient tape is what's keeping track of the gradients here. So you don't have to manually define the derivative, and you don't have to do this sort of plus or minus some epsilon. It's just automatically understands these operations and how they interact and what their derivatives are. So what this is showing is saying basically inside of this context, run this thing, and in the background, it's saying keep track of all of these things in order to say what the gradient is. So in this, they're showing using this method, saying just give it some epsilon up, some epsilon down. What's the value for these two different variables? It gets roughly the right value, but not actually exactly. And with this, the gradient tape, it gets exactly the right value just automatically, and you didn't have to do any math or like manually calculate it for every single variable in the function or anything like that. So one of the things that they point out is that the way that this tape works is it just has a certain history, and when you go pull a value from it, it's like popping off of the list, so you can't pull it multiple times. So you define these values, and then you go check it, and then the next time you go to check it is actually gone because it's been popped off of the list. So the way that you can get around this is you can say persistent equals true, and then it will keep it even when you go check it multiple times. I'm not entirely sure why that's the default. I feel like it's useful to have it persistent most of the time, but maybe saves you memory or something like that.
So just a little color here. Like Ryan said, this is probably the most useful thing about using one of these neural network frameworks. I love, there's an appendix in the book, I think it's Appendix B, that actually explains how automatic differentiation works and how it does everything. So if you're curious about it, I never understood it until I read that appendix and I was like, oh, wow, this is really cool. And there's other stuff online that explains it pretty well too. But so then you don't necessarily need to know this to use this stuff, but it's like, I find it very useful to have this background intuition. And then we started with just constants, which made life simple. So a TensorFlow constant is pretty much just like a NumPy multi-dimensional array. It's just a storage location where you've got some numerical values. Okay. What makes a variable different is that the variable has like, I don't know the exact details, but like a linked list that then will point to all the computations that happen to that variable. And so when you do this gradient tape business, it's basically going through this computation graph and it's finding the graph of all the computations. So in this case, it says calculate the partial derivative, wherever that line was, partial derivative starting with z, getting back to our C1 and C2 or whatever, W1, W2, whatever it was called. So basically what TensorFlow is doing behind the scenes is saying it's find this whole computation graph, and for each individual piece, there's a partial derivative. And then if you multiply all these partial derivatives together, then you ultimately get the partial derivative of z with respect to weight W1 and whatnot. And so that's what it's doing automatically all behind you. And that's why you need fundamentally a different data structure for a variable than a constant, because a constant doesn't care what happens, and a variable has to connect to the computation graph. And so it has some extra data structures. So I don't even know how you can do it, but if somehow you can look under the hood, you'll see that a variable just has like the obvious storage for the multidimensional array, and then this extra stuff, these lists or whatever that get populated when you do stuff. And I'm super thankful that they keep track of all that, and I don't have to keep track of any of that.
Yeah. So they're showing that this gradient tape, I was talking about the persistent part. So they're showing that if you want to specifically track certain things, then you can do tape.watch. And so this might be, I want to like specifically manage the gradient of certain variables or something. And so you can just wrap them with tape.watch. And then what it will do is it will say, okay, we have some gradients with respect to z, and then we also have C1 and C2 variables that we're keeping track of as well. So showing the same examples with that, and then they show we can also go to the Jacobians and the Hessians. Those not very common. I wouldn't really worry about those. So it's showing that we can also do it inside of our custom function. So we had that mySoft+ activation function that we defined earlier. And so it's showing like, look, we can actually like tunnel into all of these other operations that are happening in the background as well. So one of the things that they were showing is that sometimes you might want to actually calculate some value, and that might be unstable or not exactly the way that you want to do it for calculating the gradient. And so you can do something like this, where you say during the regular operation, actually do the regular exponent, but then when you're calculating the gradient, for some reason, you might want to calculate the gradient in some custom way because it doesn't work well numerically. So this is basically saying this custom gradient bit is saying do the same operation, but maybe in a different order or with some logarithm trick or something else in order to make it stable again. So just one of those tricks that you might do. So now they got into the custom training loop bit. So lately I've been working much more with PyTorch, and this is kind of like when PyTorch came out, this was the like killer feature really, is you have full control over the training loop. So with Keras, what we've seen is you do that dot fit, and then it's just doing everything in the background. And then what researchers didn't like was I actually want control of this whole training loop. I want to do some custom routine. I want it to change throughout training. I want it to, so the custom loss functions and models and activations and all of that stuff is useful, but it didn't quite give the right amount of control to things. So PyTorch came out and it gave that custom training loop, and then TensorFlow followed suit and said, "Oh, this is actually a good way of doing it." I think initially the thought was like, it's very nice to have this whole thing abstracted away, but then what people realize is like that's actually the part that we care about, and it's not really that much code to actually write the pieces out. So it's good for people to have full control over what's actually happening. So what they're showing is you can define a certain model network, network architecture. So this is the same one that we've been using throughout to find the network. And then you also say, how do I want to pull in the batches? So in the past, we just basically said dot fit, here's some data, and then it figured out how to do the batching. In this one, it's saying, here's a simple function to say, how do I want to randomly pull rows of data out of my data set? And then this print status bar is just saying, do that same kind of print out some information during training. And this saying loss function, metric. And then this is basically all that a training loop is going to be. It's like do a certain number of loops through the data, calculate the loss, calculate some metrics, and then print it out. So this is showing kind of like, this is just the template of what these things typically look like. And so this isn't an actual training run, but you can see like this is fairly simple. It's only 10 lines of code. So people realize like, actually, I don't want this abstracted away, because just writing these 60 lines lets me have total control over the thing that I'm trying to do. So these are just examples showing like what the training looks like. Hopefully this works. Maybe have to plug in a different loss function there. But this is what the training loop looks like. So you can see what it's doing is we have the different epochs. So it's saying, I want to train a certain number of loops over the data. And it's just printing off saying, okay, I'm on epoch 1, epoch 2, epoch 3 as it does training. And then it's doing a certain number of steps. So we have, I don't know, 1,000 rows of data. And so it's saying, give me a batch, give me a batch, give me a batch, however many steps that it is until you exhaust your 1,000 rows, basically. So what this is doing is saying we have this big array of data, X train scaled, and we have the set of labels, Y train, and then we're pulling a random batch from it. So it's saying grab a random 8 or a random 16 or whatever we define. And then this gradient tape is saying, okay, we're about to run some calculation, keep track of the variables, keep track of the gradients, and then we can use that in order to update our model. So this is saying basically our model is going to take some input, it's going to make some output, and then we're going to measure how good its predictions were, and we're going to try and push it towards better and better predictions over time. So we calculate the loss, and then we measure what was the average across that batch, and then we keep track of the loss there, and we're updating it over time. And then after that prediction and measurement of the loss, we're saying, okay, look at the gradient and apply that gradient. So we're saying like, okay, we need to go in this direction in order to improve our model. Now go actually update the weight in order to make the model a little bit better. And so it's looping through the variables and then saying assign these all to whatever new value. And then it's calculating the average loss. It's a streaming metric. So it's saying keep track of these losses over time. And so this whole loop is, this replaces that model.fit that we were using before. And so there is plenty of technical detail there, but if you look at it, it's like now we have total control. We can make it print out whenever we want. We can modify it to do some custom things. It's all just Python right in front of us rather than .fit. We don't know exactly what's happening inside of that black box.
Yeah, if I can add just a quick story. When I first started doing neural networks with Keras, like Ryan, like you said, pass in the data, you pass in the labels. And one of the things that tripped me up was there would be these loss functions like cross entropy, and there'd be like the one regular version, and there's the other one where it's like the log of the cross entropy, but it's more numerically stable. And so, like, you know, you are supposed to have a sigmoid or not have a sigmoid before you do the blah 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 loss function or this or that. And then I also seem to recall that for historical reasons, they weren't just named like loss and log of loss. You know, like one was called negative log loss. And so like, it's like there's this NLL thing that you're supposed to use, but this other place we use cross entropy. And it's not super obvious from the name that there's just one is the log of the other one or whatever, right? But with Keras being a complete black box, you just say fit. It was like I couldn't see whether there was an extra log happening or two logs in a row happening or whatever. And so then like with something like this, it's very clear. You can see like, okay, here's my output. There either is or isn't a log happening to it, and then it goes into this logs function. So sometimes it is nice to have that level of like, again, it's super convenient. When you really first get started, you have to write almost no lines of code, but sometimes, yeah, the automatic stuff, it's just hard to really understand what's happening.
Yeah.
So somewhere I read with the autodiff, the error has to always go, you know, it has to go down. The MAE, is that correct? Because of the way it is, the error is always going to go down, and that's the magic of autodiff.
I think what I would say is that it's configured to minimize. So it's always trying to get the number lower.
Yeah.
And so if you have something where you're trying to actually maximize it, that's kind of fine too. What people typically do is they just say, okay, I just set it to negative, and then I'm just pushing in the opposite direction. So you do have to minimize. All of this stuff is configured to minimize, but if you minimize the negative of something, it's doing the same thing. So
the reason why I asked was, I have this thing, you know, the notebook here that actually has been run before. So it was interesting. The 5 epochs, after the 4th epoch, the 5th one, the ME goes slightly higher. That function that you had, that one that you had up there on the screen, I'm trying to keep in sync with you. So that one, the 5th epoch has the MA slightly up.
So one thing I would say is you're not guaranteed to end at a final lower loss. You might hit some, this is the lowest value you can possibly hit. It's trying to keep going down, but your model doesn't have enough capacity, or your data set just has some noise in it. It's not predictable. There's many different things that could cause that. But what you do generally expect is your training loss is going to keep going down, and your validation may be much more noisy than that. So your training loss you would expect to be pretty stable, but your validation loss can be all over the place.
Yeah. And if you're overfit, your validation loss can get worse, dramatically, infinitely bad. So yes, like under good conditions, things go down and then they just stay flat. But there are no guarantees anywhere that something will not go up, that it's guaranteed to be monotonic.
Yeah. So in this one, the pattern that we can see is the training loss is going down, going down, going down, going down, going down. So it does 5 epochs. So it's not entirely clear, but this is the part that is training. So all of this is training numbers, this left column. And then this right part is the validation loss. And the validation loss, we can see it's going down, going down, going down. And then on the last epoch, it actually goes way up. It's much worse than it was before. So we would probably say that's the point where it started overfitting very badly, is making some very confident predictions that are actually wrong. This last bar that we see here is actually an additional run of evaluation. So this loss value is a little bit misleading because this is validation loss. This isn't training loss anymore. So kind of final section. What I'll say is I was mentioning earlier, NumPy, TensorFlow, very good overlap actually. A lot of this stuff maybe has slight tweaks in naming, but if you want to do operations, most of them you're going to be able to do in TensorFlow. And so one of the nice things that they've done is you can just wrap something as a TensorFlow function. So if you have something in NumPy, NumPy is great, has all these great optimizations inside of it. But then when you go to TensorFlow, it can also push it to GPU, TPU, all kinds of different computing devices. And so one thing that you might want to do is you take some NumPy function and you just wrap it in TensorFlow, and then you say, do it in TensorFlow, do it on GPU, do it on something else, and then it can magically be like way faster. Um, the other thing is it can also do certain optimizations of its own. So if you have a graph of a certain kind, it can actually go and say, oh, you're doing these things, they're redundant, prune those off, or simplify certain operations. So this TensorFlow functions is very useful. So what they're showing here is you can cube a certain value. So you say, give me X, and then put it to the third power. So they show the example. You give it 2, it sets it to 8. And you can also do the same thing with a TensorFlow constant. It works perfectly fine. But then if you wrap it as a TF function, all of a sudden you have a cube, a TensorFlow version of this cube function. So you can see it's done some crazy magic in the background and said, convert whatever you're trying to do to TensorFlow. And then if we do the same thing to just the number 2, it says, go do this in TensorFlow, go do the same operation, and then it returns the value of 8 still. And so one of the things they're showing is you can actually dig into the graph. So you make some function and then you say, okay, what is TensorFlow actually like decomposing this into and simplifying? So you can see the different operations that it's made up of. So I would say that the most useful piece of this is just knowing that you can actually do tf.function, wrap some NumPy, and then magically everything's faster. I would say that's like the majority of the value here is just like you have something in NumPy, it's running really slow. Go do TensorFlow function and see if it runs it faster. That's like the biggest takeaway here. Yeah, so they have a bunch of detail in this notebook that they actually didn't talk about in the book, so I won't go into too much detail about it. I think we've covered enough in terms of the core parts of TensorFlow and Keras. I can pause for a second. We're basically at time. Any questions? Anyone want me to go back to anything?
All right. If there's no questions, I'll just throw in one quick comment, a little bit of a cautionary tale. So normally if you're doing some big matrix multiply type neural network thing, convolutional network, all the new transformer stuff, there's lots of matrix multiplies. It runs really well on a GPU. The GPU can parallelize all that stuff. Having the freedom to write your own code is a good option when you need it. But one thing in particular to beware is if you're doing something other than math. So like it's very common that in my training route, I'll have something that says like, oh, if the step is a multiple of 100, I'm going to print something, but for the other 99 to make it run a little faster, I'm not going to print anything or whatever, something like that. But you want to be really careful anytime you have something like an if in your code, because at one point it was forbidden. You weren't even allowed to have it. Now you're allowed to have it, but it can dramatically slow down your GPU if you have something like an if, because uh, now it has to handle both branches and this, that, and is it going to split your data or whatever. So like, I think people in general know that like, oh, there's probably different ways you can write a bunch of math that some of it might run faster than others, but just wanted to kind of throw out there the biggest thing is any kind of control flow or logic that can do all sorts of terrible things. It can cause things to drop from GPU to CPU. It can cause the GPU to split stuff and whatever. And if you're doing stuff on TPUs, if you happen to be someone who uses them a lot, it's even worse than on GPUs, because GPUs have all these streaming multiprocessors and they're trying to parallelize things. For the most part, a TPU, it's just SIMD. It will only do one operation. And so what it really wants is when you say add, give me whatever the maximum number of things and I'll add them all in parallel. And when you say multiply, I'll do all that. But if you have an if, then it's going to do the two branches completely sequentially, and it can never parallel. I don't know, never is probably too strong a word, but it's really not built for that. Because GPUs were built for computer graphics, they're a little bit more general, a little bit more flexible. And so they can load some data into one streaming multiprocessor and different data into another, and they can do those things. But the TPU is much, much more optimized for just freaking matrix multiplies all day long, and it doesn't have as much flexibility.
Yeah. Thanks for the color. Kevin asked to try the Gemini button, and this is actually something I used throughout this process, so I wanted to show that for a second. So inside of the Google Colab now, they have it set up to have this Gemini integration, and so with this, I am not as familiar with TensorFlow as I used to be, and I would hit errors like this, and I can go to the documentation and I can figure out, okay, what changed, what do I need to fix about this? But the Gemini is actually pretty good at basically being like, go look at this error, figure out what it is, and you can just open up this chat box and just say like, figure out this cell, what was wrong with it. And I used that a couple times. It actually had a pop up somewhere over here where it was like basically like fix this error or like describe this error or something like that. So if anyone's ever using Colab, it's a pretty fun thing to have like directly integrated. You could go copy paste this to ChatGPT or Gemini or something, but it's nice to have it like directly bundled in, and it knows like, oh, you hit an error, like you probably want help now.
In a long notebook, do you know how to tell it which cell, if there's like different cells that have errors or whatever?
I haven't messed with it that much. I don't know. When I was running it earlier, yeah. So like it has this explain this error button. That's what I used one of the times. So it knows specifically like you're focused on this cell. So I can run this, and then it just goes and sends it to Gemini and says, okay, what's going on here? And it seems like it has access to the other cells as well, because it knew the context of like what the problem was. But yeah, this is a nice little integration in Colab.
Yeah, I think OpenAI is currently winning the number of users war with ChatGPT, but I think Google is very rapidly winning the I've integrated this into Chrome, I've integrated this into whatever Google Docs, I've integrated this into Colab, such that people are just sort of like very happy using it without having to copy paste a lot of stuff. Yeah. Yeah, exactly. And then of course you can always download your own, whatever they call them, the different browsers that are chatbots
Yeah. Yeah. the AI
inherently.
browsers.
And soon you'll be able to just tell the chatbot to buy stuff. You don't have to explicitly buy. You just like, hey Gemini, yes, this is the new sweatshirt I want. This is the new dress I want. Just go buy it, and it'll use the tool calling API to ka-ching.
So Kevin's question was, does this actually change the cell for you? So you can see it did actually say like, okay, it's running like this. Now change it to this green line, and you can basically say accept, and it will just write the code for you, or you say accept and run, and it will try to run the code right there. And if it hits another error, then you can just continue the conversation, or you say I don't like that, and you just say cancel, and it will just go back to what it was previously. So yeah, it's pretty nice integration.
That's pretty slick integration. Yeah.
All right. Thank you, everyone.
All right. Happy holidays. Stay tuned. Expecting to do a social on Saturday the 3rd. I haven't reserved a space yet, so that'll be the thing, is whether or not we actually can get room at one of the bars.